The young man at the desk was supposed to be examining patents. Piles of paper detailed new inventions for electrical devices and mechanical parts. But his mind, as it so often did, was somewhere else entirely. It was racing through the universe, chasing a beam of light. His name was Albert Einstein. In 1905, he was 26 years old and working as a third-class technical expert at the Swiss Patent Office in Bern. It was a simple job for such a complicated mind. To anyone looking in, he was just another clerk. But inside his head, a revolution was brewing. Albert found the patent office both boring and perfect. It was boring because he was brilliant and the work was easy for him. But it was perfect for the very same reason. Because the work was easy, it left his mind free to wander. While his hands were sorting through drawings of new kinds of generators, his thoughts were exploring the deepest secrets of nature. The question that haunted him was one that had started when he was just 16. He had read a book about light, and it described what it would be like to ride alongside a light wave. The image stuck with him. Now, 10 years later, he was still chasing it. He would sit at his desk and imagine himself running, faster and faster until he was moving at the speed of light, nearly 300,000 kilometers per second. He would imagine looking over at the light wave traveling right beside him. What would he see? According to the great Sir Isaac Newton's laws, which everyone had believed for over 200 years, it should appear frozen. If you run alongside a train at the same speed, the train seems to stand still. So, a light wave should look like a frozen, shimmering wave, just hanging there in space. But this idea made Albert deeply uneasy. He knew from the work of another scientist, James Clerk Maxwell, that light was a changing electric and magnetic field creating each other. A frozen wave of light was impossible. It would be like a thought that never finishes thinking, a vibration that doesn't vibrate. It made no sense. It was a paradox. This was Albert's struggle. Two of the most trusted sets of laws in all of science were disagreeing with each other right inside his own mind. Newton said one thing, Maxwell said another, and they couldn't both be right. This wasn't just a small puzzle. It was a crack in the foundation of physics. He would talk about this problem for hours with his few close friends after work. One of them, a man named Michel Besso, who had actually helped him get the job at the patent office, became his sounding board. Albert would walk through the streets of Bern with Michel, talking excitedly with his hands, trying to explain his thought experiment. Imagine, Michel, he would say, his eyes full of intensity. You are holding a mirror and running at the speed of light. Could you see your own reflection? Michel, a calm and patient man, would listen and ask questions. These conversations were like a whetstone for Albert's mind, sharpening his ideas. He had no laboratory, no university position, and no fancy equipment. All he had was his imagination, his friends, and the quiet space to think between patent applications. Then, one day, the breakthrough came. It was so simple, yet so radical, that it would change everything. He realized that everyone had been trying to fix the problem by bending the laws of light to fit Newton's ideas. What if he did the opposite? What if he started by assuming that the laws of light were absolute and unchangeable? He made two simple but earth-shattering assumptions. First, he declared that the laws of physics are the same for everyone, no matter how fast they are moving. Whether you are standing still on a platform or riding on a smoothly moving train, if you conduct an experiment, the result will be the same. Second, and this was the real shocker, he stated that the speed of light is always the same, no matter who is measuring it or how fast they are moving. Think about that for a moment. If you throw a ball from a moving train, someone on the platform sees it moving faster than you do on the train. That's common sense. But with light, Einstein was saying this doesn't happen. If you shine a flashlight from that same moving train, both you on the train and the person on the platform will measure the exact same speed for that beam of light. This sounded crazy. But Albert followed this idea wherever it led, like a detective following a clue. If the speed of light is always constant, then something else has to change to make the math work. What he discovered was that the things we think are constant, like time and space, are actually not so constant after all. He realized that for the person on the platform, time on the moving train would appear to slow down, and a clock on the train would actually, physically, be ticking slower. Not because it was broken, but because time itself stretches and contracts. Similarly, the length of the train would appear to shorten from the platform. He had found the solution to his paradox. You can never catch up to a beam of light because as you move faster, Your own time slows down, and your space contracts from the perspective of others, ensuring that you always measure the same, constant speed of light. The frozen wave was an illusion you could never actually see. In a few short months, he wrote these ideas down in a paper he called On the Electrodynamics of Moving Bodies. This was the special theory of relativity. It contained the most famous equation in the world, E=mc2, which showed that energy and mass were two forms of the same thing. He sent his paper to a famous science journal. He was just a patent clerk, but his ideas were so powerful and clear that they could not be ignored. This was a monumental achievement. But for Albert Einstein, it was only the beginning. He had solved the problem of constant motion, but he had left out one giant piece of the puzzle: gravity. The question of how gravity fit into this new, strange world of flexible space and time was now burning in his mind, leading him toward an even happier thought. The year was 1907. Albert Einstein was no longer just a patent clerk. His revolutionary papers from 1905 had sent ripples through the world of physics, earning him the attention of respected professors. He had left the patent office in Bern and was now working at the University of Zurich, his mind buzzing with a new and even greater challenge. He had built a beautiful new theory, special relativity, that fixed the problems between moving objects and light. But there was a giant hole in it, a force so common, so everyday, that his new theory couldn't explain it at all: gravity. Isaac Newton's description of gravity had stood for centuries. It was a simple, powerful idea. Every object in the universe pulls on every other object with an invisible force, like magic. The Earth pulls an apple down from a tree, and the sun pulls the Earth, keeping it in orbit. But how? How does the sun, 150 million kilometers away, reach across empty space and pull the Earth? Newton himself called this idea of action at a distance absurd, but he had no other answer. This question gnawed at Albert. His own theory said that nothing, not even information, could travel faster than light. So how could gravity work instantly across such vast distances? It was like a crack in the beautiful floor of his new physics house. He was asked to write a big, important review article to explain his new theory of relativity to other scientists. As he sat at his desk, trying to summarize what he had already done, his mind kept circling back to this problem. He felt stuck. He knew his theory was incomplete, but the path forward was a complete mystery, and then, in the middle of this struggle, it happened. He would later call it the happiest thought of my life. He wasn't in a fancy laboratory. He wasn't even at his university desk. He was sitting in his chair at the old patent office in Bern on a perfectly ordinary day. He was probably tired, maybe a little frustrated. He looked out the window, and his mind began to wander, just as it always did. This time, he imagined a man falling from the roof of a house. Not a scary, panicked fall. A calm, peaceful one. He pictured the man tumbling through the air. And then Albert asked himself a simple, childlike question. What would that falling man feel? As he thought about it, he realized something amazing. During the fall, the man would not feel his own weight. If he let go of a set of keys or a coin from his pocket, it would fall right alongside him. To the man, the keys would appear to float in the air next to his hand. They would be weightless, just like he was. This was the spark. This was the happy thought. He immediately connected it to another image in his mind, a person in a closed box, like an elevator. If that elevator were in the depths of space, far from any planet, and someone accelerated it upwards, the person inside would feel pressed to the floor, exactly as if they were standing on Earth feeling gravity. If the elevator cable snapped and the box fell freely, the person inside would float, weightless, just like the man falling from the roof. The conclusion was staggering. There is no difference between being in a gravitational field and being in an accelerating box. The force you feel when a car speeds up is the same kind of thing as the force you feel from gravity. He called this the equivalence principle. Gravity and acceleration were two sides of the same coin. This was more than just a clever idea. It was a key that could unlock the mystery of gravity. If gravity and acceleration were equivalent, then the strange rules of his relativity theory should apply to gravity. 2. He took his new key and tested it on his oldest companion, a beam of light. He imagined his accelerating elevator in space again. If a beam of light entered through a small hole on one side, what would happen? By the time the light reached the opposite wall, the elevator would have moved upwards a tiny bit. So, from inside the elevator, the path of the light would look like it was curving downward, hitting the wall slightly lower than where it started. Then, using his equivalence principle, he made the leap. If acceleration can bend light, then gravity must bend light. 2. This was a prediction that could be tested. It meant that the gravity of a massive object like the sun should bend the light from a distant star passing near it. Newton's gravity, which acted on mass, would not bend light. But Einstein's new idea said it would. The implications were breathtaking. Gravity was not a mysterious force pulling things. It was something else. If a beam of light, which has no mass, could be bent, then it meant that space itself, the stage on which everything happens, must be curved. The light was simply following a straight path through a bent universe. He was now on the trail of something monumental. He had a physical picture, a story he could understand. He knew he was right. But he had a huge problem. He was a physicist, not a mathematician. He had the brilliant, intuitive idea of a curved universe, but he had no language to describe it, no equations to write it down. It was like he had discovered a new continent but had no map to navigate it. He knew what the next step had to be. He needed help. He needed to find the mathematical tools to build his theory, and he knew just the man to ask. His old, reliable friend from his university days, the one who had always been better at the hard math than he was. His name was Marcel Grossmann. The journey into the mathematical wilderness was about to begin. Albert Einstein was bursting with his happiest thought. He had a vision of the universe where gravity was not a force, but the curvature of space and time itself. It was a beautiful, powerful idea, but it was like a magnificent symphony playing only in his head. He had no way to write down the notes for others to hear. This was his new struggle. He was in Prague now, then back in Zurich, working as a professor. The world of academia was more prestigious than the patent office, but it came with its own pressures, teaching, meetings, and the expectations of other scientists. His mind, which loved to wander freely with thought experiments, was now being pulled in a dozen different directions. He knew his physics was right, but the mathematics to describe it was a foreign language to him. He needed a translator. He needed someone who could understand his physical intuition and give it a rigorous mathematical form. And so, he turned to the one person he trusted most for this monumental task, his old friend and former university classmate, Marcel Grossmann. Their friendship was a perfect partnership of opposites. Albert was the wild-haired dreamer, the physicist who followed his imagination. Marcel was the calm, organized, and brilliant mathematician. Back in their student days, Marcel's neat and complete lecture notes had often saved Albert, who frequently skipped classes he found boring. Albert went to Marcel, who was now a respected professor of geometry at their alma mater in Zurich. He poured his heart out, explaining his radical new idea about gravity and curved space-time. He was desperate. "You must help me, Grossmann, or I'll go mad," he pleaded, only half joking. Marcel Grossmann, ever the loyal friend, agreed. He listened patiently to Albert's frantic explanations. He saw the genius buried within the chaos. "I think I can help you," he said. He then introduced Albert to a strange and complex branch of mathematics that most physicists had ignored for decades. It was called non-Euclidean geometry, the geometry everyone learns in school, with parallel lines that never meet and triangles whose angles always add up to 180 degrees, is the geometry of a flat surface, like a piece of paper. But the geometry of a curved surface, like a globe or a saddle, is different. On a globe, two lines that start off parallel, like lines of longitude at the equator, eventually meet at the poles. And a triangle drawn on a globe can have three 90-degree angles. Marcel Grossmann told Albert that this was the language he was searching for. The mathematics of Bernhard Riemann and others described how any space, no matter how curved and twisted, could be mapped and measured. This was the tool Albert needed to describe how mass and energy warp the four-dimensional fabric of the universe. For Albert, this was both a salvation and a new kind of prison. He was saved because he now had a map for the wilderness. But he was imprisoned because the mathematics was incredibly difficult. For the next 3 years, this was his life. He and Marcel became an official team, publishing joint papers. Albert would provide the physical insight, the physics of the problem, and Marcel would provide the mathematical machinery. Their collaboration was intense. Albert would work furiously, trying to bend this new math to his will, often making mistakes. He would then take his scribbled, chaotic ideas to Marcel, who would patiently show him where he had gone wrong and point him in the right direction. It was a grueling process. Albert later described these years as a time of immense strain, where he was constantly working, his mind never at rest. The pressure was immense. He was racing against other brilliant minds, like the famous German mathematician David Hilbert, who had also become interested in the problem of gravity and was quickly closing in on a solution. The First World War had broken out, cutting off communication between scientists in different countries and adding a layer of isolation and gloom to his work. His personal life was also in turmoil. His marriage to his first wife, Mileva, was falling apart under the strain of his single-minded focus and their growing differences. The man who was trying to understand the cosmos was finding it difficult to manage the complexities of his own earthly life. He published several versions of his theory, each one getting closer, but each one still flawed. In one version, he made a mistake in his calculations and convinced himself that starlight would not be bent by the sun's gravity, a direct contradiction of his own happiest thought. He later had to publicly correct this embarrassing error. He was exhausted mentally and physically. The beautiful, simple picture of a man falling off a roof had led him into a jungle of complex tensors, covariant derivatives, and curvature symbols. There were moments when he felt he was on the verge of a nervous breakdown, but he refused to give up. He knew he was close. In the final months of 1915, he was like a man possessed. He was scheduled to give a series of 4 lectures about his work at the prestigious Prussian Academy of Sciences in Berlin. He used these lectures as deadlines, forcing himself to find the final correct form of his equations. The first lecture in November presented a theory that was still not quite right. He was still struggling. He worked feverishly in the days between lectures, correcting, calculating, and rethinking. It was an agonizing public struggle. Finally, for his 4th and final lecture on November 25, 1915, he had it. He stood before the Academy and, with a quiet confidence that replaced his previous frustration, presented the completed set of equations for his general theory of relativity. The equations were elegant and powerful. They stated, in a precise mathematical language, how the universe works. The presence of matter and energy tells space-time how to curve, and the curvature of space-time tells matter how to move. The sun doesn't pull on the Earth. It creates a valley in space-time, and the Earth simply rolls around the rim of that valley, like a marble in a bowl. He had done it. He had emerged from the mathematical wilderness. The symphony in his head was now written down for all to see. He had his theory, but a theory, no matter how beautiful, is just an idea until it is tested against reality. And so the quiet physicist now had to wait for the world to prove he was right. The war was over. For 4 long years, the world had been torn apart by the First World War. In Berlin, Albert Einstein, now in his late 30s, was living in a city scarred by defeat and hardship. But in his mind, he was at peace. He had completed his general theory of relativity in 1915, a towering intellectual achievement born from a decade of struggle. He had presented his equations to the world, but for him, the work was done. He was quietly, utterly convinced he was right. His theory made a bold and testable prediction. He had calculated that the sun's immense gravity would bend the fabric of space-time around it. This meant that the light from a distant star, passing very close to the sun, would follow this curved path. To an astronomer on Earth, it would look as if the star had shifted slightly from its usual position. The only time you can see stars right next to the sun in the sky is during a total solar eclipse, when the moon blocks the sun's blinding light. Einstein proposed that by photographing the stars around the eclipsed sun and comparing their positions to a photograph of the same stars taken at night, you could measure this bending of light. But there was a problem. The world was still broken by war. Einstein was a German scientist, and most of the leading astronomers who could test his theory were in England, a nation that had just spent years fighting Germany. Scientific cooperation was almost unthinkable. However, the power of a great idea can sometimes bridge even the widest divides. The man who would become the hero of this story was a British astronomer named Arthur Eddington. Eddington was the director of the Cambridge Observatory, a Quaker and a pacifist who had deeply opposed the war. He was also one of the few people in England who could actually understand Einstein's complex new theory. He saw its beauty and knew it had to be tested. Eddington convinced the British scientific establishment that this was a mission of supreme importance, beyond national rivalries. He planned not one, but two expeditions to different parts of the world for the eclipse of May 29, 1919. This was a huge gamble. Eclipse expeditions were expensive, difficult, and risky. The weather had to be perfect. One team, led by Andrew Crommelin, would travel to the town of Sobral in Brazil. The other team, led by Eddington himself, would journey to the remote island of Principe, off the west coast of Africa. The journey to Principe was an adventure in itself. Eddington and his assistant sailed from England, their equipment packed carefully in crates. When they arrived on the island, they set up their telescopes in a clearing, surrounded by jungle humidity. They had one chance. The eclipse would last for just a few minutes. Back in Berlin, Einstein waited. He wasn't a man who showed much anxiety. When a student asked him what he would do if the results did not confirm his theory, he replied with a calm confidence, "Then I would feel sorry for the good Lord. The theory is correct." He had seen the logic of it from his thought experiment of the falling man to the complex mathematics. For him, the result was inevitable. On the day of the eclipse, May 29, 1919, things did not start well for Eddington. The sky over Principe was covered in thick clouds. As the moon began to move in front of the sun, the world grew dark, but Eddington and his team couldn't see the stars. They were photographing a blank gray sky. It seemed the entire expedition would be a total failure. Then, in the final moments of totality, the clouds briefly parted. They had just a few precious seconds to expose their photographic plates. They took 16 pictures in a frantic rush. The eclipse ended and the light returned. They had no idea if their photos had captured anything useful. Meanwhile, in Brazil, the team at Sobral had clearer skies, but they faced their own problems. Their main telescope had a technical issue that made the images slightly out of focus. They had to rely on a smaller backup telescope. The data was collected, but it was messy and uncertain. The teams packed up their delicate glass photographic plates and began the long journey back to England. The real work was about to begin, the painstaking process of measuring the tiny shifts in the star positions. For months, the data was analyzed. The world knew an experiment was happening, but no one knew the result. Eddington carefully measured the plates from Principe. The shift was tiny, less than the width of a human hair seen from a meter away. But it was there. The stars had moved. The light had bent. The data from Brazil, once all the issues were accounted for, confirmed the same result. The numbers came out almost exactly as Einstein had predicted. Newton's gravity would have predicted only half the amount of bending that was measured. Einstein's theory had triumphed. On November 6, 1919, the moment of truth arrived. A historic meeting was held in London, at the Royal Society, with the Astronomer Royal presenting the findings. The Great Hall was packed with scientists. Eddington presented the data clearly and methodically, showing the photographs and the measurements. The evidence was undeniable. The president of the Royal Society, Sir J.J. Thomson, stood up and made a famous declaration. He said that Einstein's theory was one of the greatest achievements in the history of human thought. It is not the discovery of an outlying island, but of a whole continent of new scientific ideas. The next morning, the world woke up to the news. The headline of the Times of London read, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Almost overnight, Albert Einstein became the most famous scientist in the world, a global icon. His name was in every newspaper. People who knew nothing about physics were fascinated by the man who had discovered the secrets of the universe. He was no longer just a professor. He was a symbol of genius. For Einstein, this fame was strange and often annoying. But the core of the story was not the fame. It was the journey. It was the story of a curious patent clerk who dared to chase a beam of light in his imagination. It was about his happiest thought of a falling man. It was about the struggle with his friend Grossman through a jungle of mathematics. And it was about a bend in the starlight, witnessed by determined astronomers on a remote island, which finally showed the world that space itself could bend. The universe, it turned out, was far more strange and wonderful than anyone had ever dreamed.